Hi everyone, my name is Tony Lei, and I am representing my fellow researchers Sheila Suchipto, Yujun Lai, and Gavin Paul today to talk about our intuitive virtual reality based control of a real world mobile manipulator for the 16th International Conference on Control, Automation, Robotics, and Vision, or ICAR-CV 2020. Our research presents an integration of virtual reality, or VR, with the control system of a mobile manipulator to facilitate a natural and intuitive method for human-robot interaction. Two experiments were also conducted, one to compare user performance between a traditional 2D interface and a VR interface, and one to measure the effect of control latencies on user performance for an online robot teleoperation scenario. So a bit of background on the project. As you all know, robots are being deployed all over the world. Robots can carry out activities perpetually with high repeatability and accuracy and perform dangerous tasks in hazardous environments. And that will significantly reduce the risk of physical injury. Conversely, humans can exploit expertise and experiences in their fields to make crucial choices, providing creative and innovative solutions. Therefore, a robot system can achieve more productivity by adapting a form of human-robot interaction, most commonly in the form of robot teleoperation. But there is a problem. With traditional remote robot teleoperation methods that rely on 2D interfaces, such as control panels or graphical user interfaces, it can be confusing for operators of complex systems. During robot teleoperation, a constrained view of the robot status and limitations on translating user input into robot controls has been shown to reduce task performance. Such systems often require extensive training and knowledge due to the limited visual feedback provided and unorthodox methods of interactions employed. Furthermore, the elimination of human operators from their respective dangerous working environments also removes the instinctive localized perspective. For example, for high-powered robots, the human operator cannot be in the same space as the robot working area. On the other hand, VR's ability to track movements in 3D space and translate performed motions provide an intuitive platform to explore and interact with a virtual environment. And therefore, VR provides an interface that leverages innate human actions to manipulate various aspects of the environment. These advantages make VR a suitable platform for robot teleoperation, improving visualization and reducing both the background knowledge required and the control limitations caused by physical distance. So our objective is to employ these benefits of VR as an immersive and interactive platform to use as a control interface for a mobile manipulator, which is complex by design, to create a more natural and intuitive human-robot interaction experience. Researchers have investigated human-robot interaction methods that enable natural actions in the real world to be expressed in VR. This includes visualizing in 3D the robot's intention and future positions. In these applications, the operators usually inspect the robot and its environment either with a robot-centric view, where user can walk around the robot, or an egocentric view when the user assumes a first-person view, as if they were the robot. The use of VR has also been shown to help users to predict potential collisions, as they have better spatial awareness in 3D, and VR peripherals such as the controllers that come with the most common VR headsets have their position tracked in 3D space, which can be used for applications such as robot path reprogramming, for programming by demonstration task, or making appropriate adjustments after the robot has finished its path planning algorithm. Studies comparing 2D interfaces to 3D interfaces, such as VR or AR, have shown a significant increase in both user task performance and a reduction in workload for robot teleoperation tasks. And this is the overview of our own system. We have the real mobile manipulator that we developed and built for an industry partner. It has a UR-free industrial robot arm at the front, which is a 6 degree of freedom robot, and its own control framework to control the motors on board. We also built a simulated version of the robot in Unity 3D, and we were able to get a realistic physics-based simulation of the robot. Similarly, the control schemes of both the mobile platform and the arm were carried over, which allowed operators to seamlessly transition between controlling the real one and the simulated one. The VR interface or headset that we are using is an Oculus Rift S, and also paired with are the Oculus Touch controllers. The headset provided pose tracking in 3D space and updating the view of the user accordingly. When in VR, users can view the 3D models of the controllers, or alternatively have virtual hands that they can use to grab and point at objects in the virtual environment. And finally, the control method that we use to control the arm is resolved motion rate control, which was programmed in MATLAB, and we control the arm using joint velocities. And finally, the glue that holds it all together and handles all the communication between components is the robot operating system, ROS. And we also use a package called ROS Sharp to handle communication between ROS and Unity. The first experiment was designed to investigate the intuitiveness of a 3D VR interface in comparison to a 2D interface manipulated by a mouse and keyboard. Participants were asked to perform a robot control task that resembled a practical and relevant use of the mobile manipulator. Users were asked to manipulate a detached 3D model of the end effector tool, called the waypoint marker, to guide the robot towards a desired end effector tool pose. Users were also asked to indicate when they had completed the task, with the goal specified as close as possible and as quickly as possible. We had a total of 10 volunteers for the experiment, and on average, participants reported little experience with VR and an intermediate level of experience with working with robots. So here are the two interfaces. With the 2D interface, the participants use a flat screen monitor to view the scene, and the keyboard and mouse to interact with the view of the scene and manipulate the waypoint marker. With the 3D VR interface, participants use an Oculus headset to view the scene and could change their perspective by just naturally moving their heads around in 3D space. To move the waypoint marker, users could reach out and grab it with either hand, and they could see their virtual hands in VR performing the grabbing action. This is the results from the experiment. The task accuracy was defined as the difference or the error in position and orientation of the center of the end effector tool between the manipulated robot and the desired robot. So in this graph here, lower is better, as that means a smaller error in both position and orientation. We also measured task completion time, and that was determined as the elapsed time between when the pose appeared for the user and when they decide to press the button to indicate task completion. And we also see that users completed the task with significantly less time when using the 3D VR interface as well. And finally, to measure subjective cognitive workload, we used the NASA TOX score, which measures the workload on 6 subscales like mental demand, physical demand, temporal demand, effort, frustration, and performance. And we can also see that participants reported notably lower cognitive workload with the 3D VR interface as well. The second experiment was on the effect of control latency on task performance. Participants were asked to do the same task but in 3 different control latency scenarios. Minimum latency, which is almost real time, medium latency, which is 500 milliseconds, and high latency, which is about 1000 milliseconds or 1 second ping. And we also observe a drop of mean position accuracy as indicated by the rising error as we increase the latency. And this relationship between latency and mean position accuracy approach statistical significance. However, there was no significant change in orientation accuracy between the different levels of latency. There was a 38% increase in users' mean task completion time from minimum latency to the highest level of latency that we applied. And this data also partially supports the relationship between latency and performance. However, statistically significant relationship was yet to be established. There are other interesting further discussions from the experiment. We analyzed and compared the performance of different user groups. We analyzed and compared the performance of different user groups based on their experience with working with robots. Intermediate users performed better than the novices users as expected. However, when using the 3D VR interface, novice users were able to perform at a significantly closer level to the more experienced users compared to when they were using the 2D interface. This further reinforces the use of VR as an intuitive universal interface between humans and robots. The experiment on the effects of various levels of latencies in a robot live servoing task have shown that a real-world online robot teleoperation can significantly benefit from a higher level control system. An over-the-internet control robot would suffer from high and varying latency on both ends and would require a certain level of semi-autonomy to operate continuously and effectively, even with humans in the loop. Our research presents a novel and intuitive VR-based control interface for a real-world mobile manipulator. The interface utilizes natural actions to let users perform a live control task in an environment simulating online robot teleoperation. The experiments conducted provided empirical evidence that users achieve significantly better results via a 3D VR interface than a 2D interface with mouse and keyboard. Additionally, the results showed effects of latency on user experience and performance on lower-level online control robot systems. In the future, there are potential improvements over the existing interface that can be implemented. There is also the need to develop a semi-autonomous control system on a robot that incorporates sensor data and to implement additional higher-level VR control functionality. Thank you very much for listening to my presentation, and if you have any questions, feel free to contact me at this email address. Thank you.